All right, so welcome everybody to November's StaPH-B call. We're excited to have you all here. There's a lot of familiar faces and a lot of new faces. Our friends from Spheres joining us for this call. We're very excited to have everybody on, and we are excited to kick things off. So I'm gonna go ahead and pass over the controls, the reins over to Angie, who has a presentation ready on UShER. And we're going to be learning a lot about lineage calling through UShER, how it's maybe similar or different to the machine learning models that the pangoLEARN kind of software uses, maybe talk about some use cases. I know that we have Michelle, Sue, and Jade Wang from the New York Public Health Lab who are on also, who've done some interesting work doing some comparisons and stuff. So I hope that we'll be able to see some of the work that they've done as well on this particular call. So I'm not gonna blab on too much longer, and I'm gonna pass it over to Angie. So welcome to the call.
Thank you, Logan. Yeah, thank you very much for inviting me to present about this. So hopefully everyone can see my slides now. Okay, so yeah, I'll be speaking about pangoLEARN's new UShER mode, well, new as of this year. All right, so as background, I'll talk a little bit about what UShER is, about the big tree of pretty much all SARS-CoV-2 sequences that we've been maintaining at UCSC and extending using UShER. I'll talk a bit about the background of pango lineages, like where do they come from? How are they actually defined? A bit about version 3 of pangoLEARN, and then a few more details about pangoLEARN UShER, how it works, how it's different from pangoLEARN, and then a little bit of what we expect to be working on in the future. Okay, so UShER stands for ultra-fast sample placement on existing trees, but don't waste your time looking for the H. There's no H. But basically, it's the first tool that can scale to the size of trees that we can build with the amount of SARS-CoV-2 genome sequences that we have. You know, previous tools have maximum likelihood methods that are arguably maybe more reliable when building trees with highly diverged genomes. But now we have millions of sequences, and those older tools just don't scale. But UShER uses several kind of performance hacks to do this really quickly. The first one is to pre-compute a mutation annotated tree and to store it in a really compact data structure. Once it has this mutation annotated tree data structure, then it only takes a couple seconds using maximum parsimony to place a brand new sequence based on its mutations in that tree. So it's very efficient at using multiple CPU cores to scan the entire tree to find the best placement or placements for a new sequence. And around that core placement algorithm, there's kind of a little ecosystem growing up. We have a web interface where you can upload your sequences and get their detailed placement in the tree. And extract a subtree and view it in NextStrain. There are a suite of utilities, our matutils. There's an optimization program that we use to keep crunching on the tree and try to clean up little spots that might get a little wonky as we're just extending and extending this tree. And in the GitHub repository, there are also workflows for doing various types of analysis with the public version of our tree that you can download, and then add your sequences, make your own pipeline to place them, and so on. Let me see if I still have the chat box. No, not yet. I will paste the link to these slides. There are a lot of links in the slides, so if you're curious about any of these things, I'm hoping you can, check out the slides, click on the links later. Okay, so the big trees that UCSC is primarily famous for coastal redwoods, but for the SARS-CoV-2 effort, we've been maintaining phylogenetic trees. So we have a tree that is now over 5 million sequences. We're combining all the sequences from Jade, GenBank, COG UK. Because it has Jade sequences in it, we can't just post it publicly. But if you're a registered Jade user, contact me and I can send you the tree if you want to try processing anything with it on your own. But about half of those sequences are in fully public repositories, GenBank and COG UK direct downloads. So you can download our daily updated tree with 2.5 million sequences. In our daily update pipeline that we've been running for most of this year, we start by downloading, aggregating everything that we can, trying to sort out which sequences are duplicated between Jade, GenBank, and or COG UK. Pull it all together. We do some minimal quality control and removing sequences that have fewer than 20,000 non-N bases. And then every day we pick out the sequences that are new, not already in the tree, align those to the reference. We mask sites that are known to be problematic when building phylogenetic trees. There's a GitHub repository called problematic sites that we use for that. Then we run UShER to add those new sequences to the tree from the day before. Also run MatOptimize a little bit. We remove sequences that have too many equally parsimonious placements. That means there are multiple locations in the tree where they would fit equally well. And that reduces our confidence that we can, place it in the tree and be sure that it's in its correct placement in the tree. Some sequences just have too many ends at important sites. And so we don't really know where to put them. And then we extract the public tree for our downloads. And then this was a delightful surprise of open science. We put our public tree out there for download, and then somebody in the UK made a tree viewer that's capable of viewing millions of sequences at a time. You can smoothly, scroll out to view 5 million sequences. You can smoothly scroll in to see, the detailed sample names. You can click on a sample and get its assigned lineage and its mutations and so on. You have some coloring and searching options. It's really a great tool. Yeah, just gotta love that kind of surprise when wondering like, okay, I've got this tree, but how am I going to visualize it? And then, bam, so it makes the perfect tool. Oh yeah, there's a link on the previous slide. You can go to cove2tree.org and click to view the latest daily tree and just see what's there. Okay, so I'm sure all of you are at least somewhat familiar with the letter.number.number pango lineages. They've been around for more than 1.5 years now. Initially proposed by Andrew Rambo's group at University of Edinburgh and others. There's a website, covelineages.org, that maintains like a detailed list of all the lineages, and there are like over 1,500 now. And they've expanded that to incorporate to include more volunteers. They've got people from many different countries now involved in evaluating new lineages and so on. And there's a website, pango.network, that's got all kinds of more information about lineages, like, the very detailed rules that we're supposed to apply when assigning a new lineage. They've got facts like how to suggest a new lineage. Their news site has some very useful updates on some of the new AY lineages, the sublineages of Delta. And then the ultimate authority on, how these lineages are defined is this pango designation repository on GitHub. That's also the place where if you want to define a new lineage, if you want to propose a new lineage, you file a GitHub issue in the pango designation repository. So getting down to nuts and bolts, like what really defines B.1.1.7 or B.1.617.2. It's not defined as a set of mutations. Sometimes I kind of wish it were, but the way they chose to go about it is there's this very important file, which I'll refer to a couple more times, Lineages.csv. This is kind of the final authority, ground truth on how lineages are defined. It's a file with more than 1 million lines, where each line just has a sequence name and a lineage to which it has been manually designated. So the real definition of, say, B.1.617.2 is whatever all these sequences that are associated with it in this file, whatever they have in common. So it's leaving it a little nebulous. Like, you can have different methods of determining what all these sequences have that makes them different from the rest of SARS-CoV-2 sequences. So that's a lineage definition. And then the tool that the entire world is using to assign lineages to new sequences is pangoLEARN. And it has also been around since late April of 2020. It's mostly the work of Anya O'Toole at the University of Edinburgh, who, as a grad student, just cranked out this incredible series of critical software packages for Cog UK, and that, ended up being very widely used. The first version actually used a phylogenetic tree, and I believe it used IQ tree to place new sequences to kind of add them to the existing phylogenetic tree and assign a lineage that way. But they ran into performance issues. It wasn't really fast enough to scale, maybe once they got to about 60,000 sequences, which at the time seemed like so many. So Emily Scher, also at the University of Edinburgh, and Andrew Rambo's group, came in with the pangoLEARN model, a machine learning model that is very fast, runs very quickly to evaluate new sequences. I feel that it's a little sensitive to noise in the sequences. If there are n bases, and ambiguous bases make it tough for any tool to really place a sequence phylogenetically. But I think some of the speed of this machine learning approach might come at a cost of accuracy. Meanwhile, at UCSC, we have this great tool, UShER. We're building up our tree. So I asked the group if they would consider maybe adding an UShER mode to pangoLEARN so that there could be kind of an alternative method for comparison, and they graciously accepted. So yeah, we started working on that in March, and then in May of 2021, version 3 of pangoLEARN came out. So now, in addition to pangoLEARN, there's a new UShER option, and they also added a new tool called Scorpio that uses what they call constellations. So those are files that actually define mutations that you might expect to see in a lineage. And Scorpio is now part of the overall assignment algorithm within pangoLEARN. And I'll talk a little bit more later about how Scorpio fits in. Okay, so digging into the whole pangoLEARN model a little more deeply. Here's figure 2 from Anya and Emily's paper, which was published very recently about pangoLEARN and pangoLEARN. This figure is a great summary of kind of the different phases of the whole lineage process. So Over here on the left, this is the manual designation stage, like when lineages are defined. People are looking at phylogenetic trees, extracting lists of sequences, manually designating those to lineages. Then there's a pangoLEARN training phase. The genome sequences that have been designated, and then the associations with different lineages are put into kind of a machine learning training process, and then out pops a trained model. And then this is pangolin here. So pangolin takes your sequences, a trained machine learning model, and out pops the lineage assignments for your sequences. So filling in some of the blanks in that training process, as far as I can tell, what really happens with the sequences during training, they're aligned to a reference genome. The ends are masked, so the non-coding beginning and end of the genome, pretty significant regions are just ignored, and only coding mutations are considered. The sequences are turned into binary vectors where a 0 bit means reference or N, and then a 1 bit means the alternate allele. And positions that don't vary in all the sequences or that don't vary in enough of the sequences are ignored. So then there's some scikit-learn crunching that goes on, and out pops a decision tree model. A decision tree just applies a series of kind of true or false, yes or no tests to these binary vectors. And then at the end of running the binary vectors through this binary tree, out pops the lineage assignment. And I think the theory of using a decision tree model here was that it should end up looking kind of like a phylogenetic tree. You would expect a phylogenetic tree behavior for these lineages. And they have a way of dumping out the decision tree to a text format, so you can look at the nuts and bolts. This is a link to an actual file in the pangoLEARN GitHub repository. You can unpack it, you can look at it. Parts of it look sort of phylogenetic with some mutations that you might expect to see, and parts of it look a little surprising. If anybody else has looked at this, you know what I mean here. Okay. Okay, so this decision tree model has been trained, and then when you're running pangolin, you give it your sequences. It does the same alignment to reference, masking of the non-coding ends, transforming into binary vectors and running the binary vectors through this decision tree model. This is when you get your lineage. There are analogous phases for the UShER mode of pangolin. Instead of a machine learning training, we have kind of an annotation process. We take the big tree that we're building up at UCSC. We take the lineage definitions. I'm also starting to maintain by hand a separate file with like the mutations in AY lineages and variants of concern and so on. It's a little quicker and more stable if I can just kind of feed in, like, these are the mutations that we want to look for in the tree. And then MatUtils Annotate is a program that takes all this information, and then for as many lineages as it can, based on the designated sequences and mutation input, it picks nodes of the tree. So even visually looking at the tree, I could just tell you by eye that here's the root at lineage A. Lineage B splits off pretty quickly and is most of the pandemic. This here is the alpha variant. Delta is this big blob here, and then this blob at the end is just that is AY.4, which got huge, and Cog UK produced a zillion sequences for it, and now it's a huge part of the tree. All right, but we can't just put this gigantic 5 million node tree into pangolin, because it takes at this point a few seconds to place every sequence. That's just too slow, way too slow. So we do a pretty drastic pruning of the tree. Let's see. Okay, I don't really have time to go into all of those, but basically we have a process that just picks randomly 50 descendants of each lineage and prunes everything else from the tree. And so we end up with a tree of pretty much only lineages with, some random subset of their descendants to keep a little bit of the genetic diversity within each lineage. So we go from 5 million down to maybe 75,000 sequences. And that is a lot faster and still, we hope reasonably accurate in placing your sequence in the correct lineage. Okay, so at runtime, your sequences come in, pangolin aligns them to the reference, chops off the ends, and then now it invokes UShER to place the sequence alignment in this lineage tree.pb that is now distributed along with the trained pangoLEARN model, and out pop the lineage assignments. Okay, so what's the difference between them? pangoLEARN is still significantly faster, even though we prune down the tree pretty drastically. The binary decision tree model is really fast. So if you run pangoLEARN-UShER, you can expect to kind of spend more compute cycles on it. UShER really does take advantage of multiple CPU cores. So if you can throw a lot of CPU cores at it, it can run still pretty quickly in terms of elapsed time. And underneath it all, UShER is using a mutation annotated phylogenetic tree. So, if you want, we can drill down into it, look at specific mutations, and reason about why a sequence is placed where it is in that tree and how that feeds into a lineage assignment. Okay, now, one thing you should know when you're looking at your outputs from pangolin is that regardless of whether you're using pangoLEARN or UShER, sometimes the assignments don't come from pangoLEARN or UShER. There are a couple different other sources of assignments. So the first is by directly recognizing sequences that have been manually designated. So they maintain kind of a hash of manually designated sequences, and then they hash your input sequence. And if they detect that your input sequence is identical to a manually designated sequence, then they just directly assign the manually designated lineage. If that happens, you'll see pango-v whatever in your line of output. There's also a comment at the end. It says assigned from designation hash. So in that case, it doesn't even call pangoLEARN or UShER because it says this one was already manually designated. So the other way that pangoLEARN or UShER might not end up as the source of your assignment is if Scorpio, with its constellations definitions, if Scorpio overrides the call. And there are two ways that can happen. One is if, so here's a line that has this pLearn. So this, is using the pangoLEARN model. pangoLEARN assigned B.1.1.7, but Scorpio determined that your sequence is actually B.1.617.2. So if you see this in the output, Scorpio replaced lineage assignment, then it'll tell you what pangoLEARN called it, but it will override that. And then another way, another thing to look for in output is if you have an assignment of none, that can mean that pangoLEARN assigned a VOC, but Scorpio, by its metrics, felt that the sequence does not belong to that VOC, that constellation, I should say. So since there's conflict, pangoLEARN just kind of nullifies the model assignment and puts none there. And that kind of thing can happen whether you're using pangoLEARN or UShER. So if you're using UShER and you have the pusher tag in your output, you might see the same kind of comments, Scorpio replaced lineage assignment, or lineage assignment was not supported by Scorpio. That's when you get the none. Okay. So looking forward, I can guarantee you that there will still be lots of releases with new lineages being added. You'll see changes in your outputs because more granularity is being added to these lineage definitions. I think it's likely that support will be added for more pre-computed assignments for pangoLEARN and UShER. That will be a way to get faster assignments for pre-existing sequences that they haven't been manually designated, but the Edinburgh folks can pre-compute all the pangoLEARN stuff on existing sequences, and UCSC can pre-compute UShER assignments for existing sequences, and kind of feed in a new hash that pangoLEARN can then use to zap directly to an assignment instead of running a model. And I think it's possible that we'll see expanded use of Scorpio where the mutations in the lineages are explicitly spelled out and tested for, but I'm less sure that'll actually happen, but yeah, we will see. And we'll also be working on more evaluations of pangoLEARN versus UShER. We are just getting started on that at UC Santa Cruz. But fortunately, at New York City Public Health Labs, Jade Wang and Michelle Su have already done some work on that. So we'll try to wrap up here so that they can talk about that. So yeah, for acknowledgements, Yatish Chiraki, if it weren't for Yatish, there'd be no UShER, none of this. And he's got a brilliant student now who's working on Mat Optimize, Cheng-Ye. And then pangoLEARN and so many associated tools coming from Andrew Rambo's group at the University of Edinburgh. And very, very grateful to them for being so, receptive to having a new mode added to their tool so we could try out UShER. And then my coworkers at UC Santa Cruz, Russ Corbett-Dedig as a professor who's been kind of coordinating, leading this research. His grad students, Jacob McBroom, Brian Thorlow, and Alex Kramer have added tons of functionality to Mat Utils. And Mark Perry is just getting started helping us to do more concrete evaluation of pangoLEARN and UShER. So with that, I guess I'll hand it back over to Logan and Michelle and Jade.
Well, thank you so much for that. That was incredibly detailed, and I learned so much about pangoLEARN just now that I did not even know. Yeah, and we even had the pangoLEARN folks on a while ago, but I think so much has changed, since we had them on, which was I think about a year ago, and so many different features and functionalities have been added, and so it's really helpful to kind of stay up to date with this kind of stuff. So I really am appreciative of everything that we've learned. So I can hand it over now to I don't know, Jade or Michelle, if one of you guys wants to take over, but if you can share your screen, go for it.
Yeah, I just have a quick introduction and then I'll pass it on to Michelle. First, I want to thank everyone on the pangoLEARN team and the UShER team so much for developing this tool. It's allowed us to quickly group sequences together and enable our epi partners to do surveillance with the virus in our city. So very thankful for everyone who's contributed to the development and even people who's contributed to the lineage assignments. So we started doing pangoLEARN and sharing our results with our epi partners sometime in the summertime this year. And so at the time, when we were sending the results to them and updating our pangoLEARN versions, they were seeing week to week a lot of changes in lineage assignments, and sometimes they would kind of panic and say like, oh my God, there's a large increase in AY4, should we alert the commissioner? And it was just a little bit hectic, and like every time there's like a new lineage that pops up on their radar, we had to like look into like what the mutations are and like whether the sequences were actually similar to each other or not. And it's just a lot of work that seems very overwhelming. So Michelle joined our team in September, and she suggested maybe we should look into using UShER as the results for the epi partners to look at. So Michelle started working on comparing the results with all of our sequences. So I'll pass it on to her to show you all what we found so far.
Great, thanks. So yeah, like Jade said, please wait while I pull up my slides. Hopefully everything works.
We can see your slides.
Awesome. So like Jade said, I'm going to be talking about our comparison of pangoLEARN versus UShER in discriminating delta and its sublineages. And so like Jade said, we were finding that a lot of the pangoLEARN lineage calls weren't monophyletic. So it was kind of hard for our epi partners to do association studies because they were interested in things like vaccine breakthrough. But if your lineage calls aren't reliable, then your association calls aren't very reliable. So, the question is, what is the extent of this issue in the delta lineage? So our sample set, this started in September. So at that time, New York City had about 7,000 something sequences that were delta and its sublineages. And as of early November, that is now split into 36 lineages as called by pangoLEARN. And I did remove the sub-lineages. So like no AY4, D4.1 to something. You can see on the bar graph on the right that the majority of it still is just overwhelmingly the parental lineage, which is delta. We have a lot of AY25, AY3, but there's still only like 11 lineages that even have greater than 100 sequences. So our methodology was basically, let's take these sequences, let's build a tree. So we took our consensus, aligned it. This is all, I'm sure, very familiar to you. And then we built a phylogenetic tree. And then we use pangoLEARN to call it. So over the course of like 1.5 months, we called it 7 times. So anytime pangoLEARN or any of the dependencies updated, we would download the new version from Conda and then run it again. So this runs from the pango designations 1.2.76 to 0.91, pangoLEARN versions 3.1.11 to 16, and the pangoLEARN models from September 17th to October 18th. And so when you do all of this, this is our huge tree. It's a bit overwhelming. So it was like, I don't know how to visualize this because there are just too many overlapping tips. So I was like, okay, we have to downsample this tree. So the strategy to downsample is basically for all the nodes in the tree, if you check all the tips resulting from that node, and if they have the same lineage and the same history, because we ran this 7 times, then you just pick one of them and then discard the rest of the tips and then discard, repeat if necessary. So after 6 rounds of pruning, we get our tree down from 7,000 something samples to 853, which is actually still a little overwhelming, but this was kind of about the limit that I could prune it down to. So then it's like, how does pangoLEARN and UShER compare? So at the start, this is what it looked like. So the left tree is the pangoLEARN calls, the right tree is the UShER calls, and the tips are colored by lineage. So we only have the top 5 lineages here just to make it easier to visualize. And because most of our sequences are delta, which is the lime green, you can see most of the tree is lime green. And theoretically, you want the colors to cluster together. And you can see that the trees are relatively concordant. So AY14, which is the lilac near the bottom, those cluster to one clade. It's monophyletic. And as we all know now, though, AY4 pangoLEARN was having a really hard time calling when it first came out. So you can see a lot of purple dotted along the left tree that you don't see in the UShER tree. And so, but what does it look like now, like later? This is as of early November. You can see that pangoLEARN fixed its AY4 issue, but now it's having a hard time calling AY43. So that kind of like begs the issue of like, how stable are these lineage calls in general? Because that was one of the things that really trips people up, is like, well, these lineage calls keep changing, like, should I trust them or not? So this is the same tree on the left, and then on the right is a sort of categorical heat map. So each color is a lineage call, and if a lineage call doesn't change over the from like when we started running the analyses, the left column will just show that it's static, and then on the right hand you see for each time that we ran it is a new lineage call. So you can see there's a significant portion of samples that get reassigned, which we would expect some amount of reassignment, because as more sequences come in, certain new lineages get called. So you would expect some amount of that, but overall you can see that pangoLEARN calls are not very static, which I think we all knew already. But when you compare this to UShER, this is what the UShER looks like. There's a lot more samples that are just static the entire time of this analysis. And when they do change, it's mostly that it was reassigned to a different lineage as we learned more. And as Angie was talking about, there's also the issue of Scorpio. It's not an issue. Scorpio can override these calls. So I also looked into that. What is the influence of Scorpio on these calls? And overall, from the 800 something, no, actually, I think this is all of them. So there are 207 samples that get overridden by Scorpio in the pangoLEARN out of all 7,000, and only about 36 samples that get overridden if it was called by UShER. The most common lineages for pangoLEARN are AY4, which makes sense, P1, and AY25. And the most common lineages for UShER are B1 and AY25. So it seems like maybe UShER sometimes is a little conservative, because a B1 call is a little weird nowadays. So to wrap up, it seems like pangoLEARN has become more consistent over the time period that we tested. There is clearly a learning period for new emerging lineages, such as AY4 and now AY43. Overall, UShER is more stable over time. And because of that, Scorpio is used more often to like hotfix pangoLEARN than UShER is, which really speaks to how useful Scorpio is overall. But that's it. Thank you so much. I'll take any questions if you have any. I'll stop sharing.
Thank you so much. That was a fantastic presentation. And I know some people in the chat were seeing this as well, but great visualizations. I just wanted to say, I know here in Virginia, we've done something kind of similar where we looked at the past, I think it was like 5 updates of pangolin, and then did a comparison between UShER and the pangoLEARN models, and we saw very, very similar things, in that when UShER made a change, it stayed that change, whereas sometimes with the pangoLEARN algorithm, it seems like it isn't as stable. We're seeing sometimes between all of the different versions, it called a different lineage every single time, and it's mostly, I think, due to those AYs and that learning period where there's a bit of kind of flux as they kind of settle out onto the tree. So I guess I'll open up the floor for questions. I'm sure that there's probably people who have things that they want. Yeah, go for it, Brad.
Hi, thanks. That was a really nice talk. Well, the cameras over there, the screen where it goes. I'm wondering, I got advice from Angie, I think a while back, related to a similar call back in the day. I was observing a bunch of lineages being called as the base lineage, 617.2. I could see the mutations looked like they were canonically something more specific. And I wonder, that's something you guys didn't, I don't think I saw that in your slides, that you saw that like bias toward the generic with the pangoLEARN, and then adding --UShER, in my experience, moved that you got better specificity for some of these. I don't have anywhere near the volume you have, but I wonder if you also observed that generic versus specific difference between pangoLEARN and UShER, or pangoLEARN and UShER.
I think UShER is a little more likely to go towards the basal lineage, unless there's a really kind of slam dunk case for one of the deeper lineages. But actually, I would love to look at examples if you could send some sequence IDs or anything. Sure. where like if you think it really belongs on one of the more detailed branches, or we're not placing there, I'd like to look into it.
It was, and I noticed that I saw that UShER did it did what I thought what I would have done by eye. I thought --UShER seemed to be more specific, which is what I
okay.
Like a couple of anecdotal cases there. Sounds like that's maybe opposite of what you're expecting in general for UShER, but maybe the anecdotes don't really give us much.
I've seen it go both ways. Yeah, well, yeah, we are going for more accuracy. So I'm hoping that you will get the correct lineage, whatever that is, whether it should be more basal or more detailed. But our tree is not perfect. So yeah, I don't know. But if you ever see anything that looks broken coming out of UShER, please tell me. I'll try to fix it.
Great, thanks.
Go ahead, Kevin.
Hey, I had a question, Michelle. That really was fantastic visualizations showing the stability, especially the one that showing the changes after every release. And so I have a question on what you're doing in New York, and Angie, maybe you have a perspective of what's happening even with the larger databases, SARS-CoV-2 genomes, about when these releases get made available. Is it appropriate to recall everything, right? Because at first, that's kind of, even to some extent, that's what we're supporting with different laboratories, where you have tens of thousands of samples or something like that. But as the sample volumes continuously grow, even though it's a small compute cost, it's non-zero per sample. And we're talking about 5 million samples. It can get rather large. So I don't know if there's a framework of how far back do we need to recall things as these new updates become available.
Yeah, I think that's a very good question. During the summertime, we had a lineage B1621 and B1623. Those lineages had some overlap. So some sequences were getting called B1623, even though they were more similar to B1621. So we had submitted an issue with the pangolin group, and B1621.1 was created, but the labs around New York City were still submitting results with whatever version they were working with, and they didn't get to update their data. So we had like some data that was coming into New York City labeled as B1623. And our epi partners are saying like, oh, hey, there's a sudden increase in B1623. What is going on? And when we looked at the actual sequence and reassigned these, they were actually B1621. So, you know, I think in terms of like making sure there, if your whole data set is analyzed using different versions, it's kind of difficult to assess whether there's a true increase in a specific lineage. And I think the only way we can really update that is to be able to reanalyze things, right?
Yeah, I agree. And that is the conversation we have with most labs. Like, well, we've made workflows available to just update your lineage call as per the newest Docker release that Curtis has put together. But yeah, so that is in line. But I do wonder, given the growing volumes and like, especially when you're comparing things to the GISAID tree, for example, and they're using pangoLEARN, you know, for their lineage calls. And yeah, so thank you for that. Angie, I don't know if you have a perspective on that as well. Yeah.
Yeah, that's a really good point. There is a cost to it, but the Edinburgh folks just came up with an idea to help with that. I mentioned it really briefly on like my last slide as a possible area of work for the future, but they have this idea to for the respective groups to pre-compute lineage assignments and then kind of make those available as part of pangoLEARN, so that if it recognizes a sequence that has a pre-computed assignment, it will just call that instead of calling pangoLEARN or calling UShER. So hopefully that will really reduce the computational cost of reassigning all your old sequences. If they're in GISAID or GenBank or whatever, that should make it a lot more speedy and therefore cheaper.
Yeah, and it might be also in how we're invoking pangoLEARN, in that we have like single VMs doing it in parallel, but rather than using like the full input of like you can do multiple samples at once, and what Danny was describing there, and then that can drastically reduce the cost. And what he's showing, they're like 70,000 genomes for like $9 or something. That will relieve all my my issues there. So thank you, and thanks, Danny.
So I had a question. On one of your slides, you said that you were manually curating mutations. Are you doing that for all of the lineages, or that's just for like a certain subset to help with like the classification?
For now, just the AYs and the WHO Greek letter variants. That's the set that I'm maintaining by hand. But Chris Roos, who's the one who's been cranking out these AY designations for the Pango network, is I know he's working on a script that will generate constellations files for Scorpio that actually list the mutations that are in each of these newly designated lineages. So we'll, yeah, hopefully we'll see more kind of explicit listing of mutations from that.
Thanks. Yeah, that would be really helpful, I think.
Cool.
Were there any more questions? Oh, I see Kim.
Hi, I'm Kim from the University of Idaho. I'm curious if you guys could comment on how people are seeing some issues with consistent amplicon dropout and consistent artifacts in the data that's being generated by various different library prep methods and sequencing methods. Just curious on your comments on how those are affecting lineage designations and how concerned we all should be about it and how much effort we should be making to you know, change our library prep methods to get rid of some of these artifacts.
Okay. I would say it's not only the library prep, but also the bioinformatics side, the genome assembly pipeline. I see all kinds of problems that I believe could be prevented by appropriate trimming of primers, adapter sequences. There seem to be some genome assembly pipelines that don't do enough trimming. And then those cause a lot of spurious, you know, apparent mutations that aren't really mutations. And yeah, so that when we're building the UShER tree at UCSC, we mask problematic sites. That's the, there's a GitHub repository called problematic sites, and it attempts to keep track of all these sites with like known sequencing issues. So that does mean that our tree is missing some of the mutations that we know are in some of these lineages. Like, so due to amplicon dropout, we are masking the spike position 142. So we know that Delta has, you know, spike one, I guess it's D142G. You won't see that in our mutation lists, kind of dumped out from our mutation annotated tree. Yeah, it's tricky. Masking is the way we deal with that so far. We just totally ignore those sites in the genome when building the tree, but
Angie,
you do lose some information there. Yeah.
Yeah, if I may. So the problem with having a full list of problematic sites, some of these problematic sites are very specific to the primer set used, to the pipeline used. So if you do this, you're losing information that might be good as well.
Yeah, that's true.
And sometimes like being able to compare data from multiple pipelines kind of gives you confidence in one call versus the other, or kind of highlight the problems. And that is why like having raw data available in SRA, having the full metadata there associated with it, which tells you which pipeline you used, what thresholds you use, what primer set you use, can be helpful to the community. Depending on where, even sequencing technologies, everything needs to come in. There's so many issues here with some pipelines filling in with reference sequence, some pipelines not calling insertions even though they're in 1% of your reads, or deletions. And similarly, it's like all kinds of wide variety of things. So one of the ways is user beware. Like if you're using data from public repositories, don't just go by everything. You have to validate things. Yeah.
I should mention, Mike, to clarify, I forgot to mention that all the sequences that I've been looking at where I saw that increased specificity from UShER were sequences generated with bar skips, so we have full coverage. And I think pangoLEARN was having trouble with the sort of, they had been trained on all Arctic 3 data, I think, or the bulk of the data is Arctic 3. And so I think that's probably why we're seeing more trouble. I think that's consistent with what Angie was explaining about why that's not happening with the UShER mode, because it's not considering those dropout regions. But I think they want to make a really good point that that's a bummer, because we'll have no more genome left if we mask out everything that's problematic somewhere at some point. So it'd be great to get that metadata, there. I've got a proof of concept tool that can infer it from raw coverage, can infer the amplicon scheme from raw coverage. But I would love to collaborate with somebody who has some more compute energy than I do at the moment to process all of this SRA with that and try to classify it. So if anybody's interested in collaborating with that, please reach out. Okay.
We have a few minutes left, and I know that this call backs up to another call that a lot of people on this call will want to be on. So I want to make sure that I get to everybody that I can before we end. Were there any other questions? I had a question about how you were assigning problematic sites. Is that just something that you guys are doing kind of manually, and are there different like categories that would, I mean, that's probably a whole discussion in and of itself, but.
Russ, I saw you in the chat. Maybe you could address that really quickly. yeah, there are people from several different groups who contribute to the masked sites repository. I know our group has contributed some of the sites, but not all of them. Yeah, Russ has been more involved in determining those. There's a publication on Virological about those. So let me again, I'm gonna paste my slides link into the chat. There's a link to the problematic sites repository in there. Lots of good links in there.
And there's one to the virological article.
Oh, perfect. Yeah, we can take a look at that there. Well, thank you. I guess in the kind of last minute or so that we have before we kind of wrap up, I just wanted to say that this recording will be made available on our website, the StaPH-B.org. So it'll be in the videos tab. And then, yeah, I mean, if it looks like, Angie, you have a link to your slides. So would it be all right if I linked the slides to the video there as well?
Absolutely. Yeah, thanks.
Perfect. Yeah. So then we'll make that available there as well. In the last couple of minutes, yeah, I just wanted to say thank you so much to all of our speakers. It was a great presentation. I think a lot of really good information and a lot of really good questions and discussions afterwards. So I just wanted to extend our gratitude for you guys being available today. If there's any other things, can people reach out to you by?
Oh, definitely. Yeah, I'm on the SpHER Slack and the StaPH-B Slack and microbiome info, or Angie at soe.ucsc.edu. Yeah, if you see anything weird or have questions about UShER, like, yeah, definitely give me a ring.
Awesome. Yeah, so multiple ways. Well, thank you so much, everyone. I'll stay on for a little bit just in case there's any other people who want to say anything, but otherwise, happy Friday, and thank you so much for being on the call.
Thanks so much for the invite.
Thank you.
This was fun. I'll hang out too, just in case anybody has any other questions.